All right, we are going to be getting into our titration curve calculations. Today we're going to focus on taking a weak acid and titrating it with a strong base. This introduction part I went over in the first video that I posted, so make sure you watch that first. It just talks about the different segments of this curve and the calculations that are going to go along with it. So our question here is, what is the pH at each of the following points in the titration of 25 milliliters of 0.1 molar acetic acid by 0.1 molar sodium hydroxide, and gives us the Ka of the weak acid. One thing you always want to keep in mind is you want to know where the equivalence point is in the titration. Now, they have equal molarities, so we could figure out the 25 milliliters, but again, it's good to practice kind of the steps along the way. So you'd want to write out your balance equation, start with your volume of your weak acid and its molarity, the balanced equation, the stoichiometry, and then figuring out your liters or milliliters of your strong base. So that would be at our 25 milliliters. It's also good to know where your half equivalence point is, which would be half of that volume, so 12.5. And you can see I also took the negative log of the Ka to get my pKa as well. So just some kind of introductory things, so that way you know if you're before, at, or after the equivalence point. So our first calculation is before any addition of sodium hydroxide. This is just going to be our initial pH, which is just the pH of a weak acid. Okay, so for this I'm going to have just I need to figure out my hydronium produced from the ionization of my weak acid. I'm just going to leave out phases. At this point you should have a pretty good idea of all of them. And we did this in the last unit, so I'm not going to take too much time on this part. So I'm using my ice table. So I have a 0.1 molar acetic acid. I'm going to plug in 0 for hydronium because we know that that percentage of from the autoionization of water is less than 5%. And then it's going to be proceeding to the right, so I can fill in my appropriate X values and then combining them for their concentrations at equilibrium. This is where you're going to use your Ka, so 1.8 times 10 to the negative 5, and then your concentration of your products over the concentration of your reactant. Okay, a couple things. I'm going to first cross out and simplify my math here. So we're going to say that the change of X is going to be less than 5% of the original concentration, so I can simplify that. Going ahead and solving for X, and I'm actually going to use the 3 sig figs from the concentration here and not the Ka expression. X is going to be the concentration of hydronium. It is also the concentration of my conjugate, but I'm interested in the hydronium to get my pH here. And then keeping in 3 sig figs, I get 1.34 times 10 to the negative 3rd molar. And then I use my amount in my calculator. I didn't round it off when I actually was using it to calculate pH. When I take the negative log of that calculator answer, the pH that I get is 2.872. Okay, so this would be my pH of my weak acid before I start the titration. All right, so part B here, after the addition of 10 milliliters of the 0.1 molar sodium hydroxide. So at this point, I know that I've added in some base. Now I know my half equivalence point hasn't been reached yet. So one thing with that is we know that we're in our buffer region. So I'm going to end up using the Henderson-Hasselbalch equation. I'm going to do a little bit with stoichiometry first. Also keep in mind that because it's before the half equivalence point, my pH is going to be less than my pKa. So I should see that my concentration of, my weak acid HA should be greater than the concentration of its conjugate base here. Just something to keep in mind, and we'll check it as we go. All right, so let's start with our weak acid. Now, with our weak acid, the idea here is that it's going to be undergoing neutralization. I'm titrating with a strong base, so it's going to be reacting with hydroxide and forming its conjugate. All right, so ICE. Now for this, I'm going to be using this in terms of moles here. So for my moles of my acetic acid, I just have to know that it's 0.02500 liters, and it was a 0.1 molar solution, so I get 0.0025 moles of it. So I'm going to start with that. Okay, and then I also need to know my moles of hydroxide. So I have right now just 10 milliliters of it. And it has also 0.1 molarity. So I have 0.00100 moles of the base. Mole. Okay, and then 0 for my weak base to start. So all of the hydroxide is going to react with my weak base. So this is X. So my amount of hydroxide here is going to be my X value. So it's going to then produce that amount of my conjugate. So for the moles of my weak acid that's still present, I have 0.0015 moles. I'm going to have 0 for my base. And then I'm going to have 0.001000 moles of its conjugate. So then this is where I can do my Henderson-Hasselbalch equation, because I have weak acid and its conjugate in solution. So I'm going to have my pH is equal to my pKa plus the log of the conjugate base over the weak acid. Okay, so my pKa is 4.74, which I figured out from the Ka earlier. And then I'm plugging in the log, and then make sure you plug these in the correct spot. 1,000 moles. Now, we talked about when we did buffers that ideally, and actually I feel like I'm missing a 0 up here. Ideally, you would be using molarity there, but it is appropriate to use moles because of how the volumes cancel out, since they're both in the same volume, or in terms of both of them being in the same solution amount. And then I'm going to keep this, which really I guess we have 4 sig figs here. So if I plug this in, 4 point plus the log of 0.00. Okay, I am going to get 4.5631 as my pH here. Normally you wouldn't see the pH that precise of a number, but just keeping with sig figs here. If you had 4.56, sorry, that's supposed to be a 9.64, that would be appropriate as well, based just on the concentration that we were dealing with up here. All right. So that's your kind of before you're halfway to your equivalence point. We have a buffer solution. You can see that this did hold up. You have more of your weak acid present than your weak base, and we were able to use the Henderson-Hasselbalch equation. So in part C here, it says after the addition of 12.5 milliliters of our sodium hydroxide, that is our halfway to equivalence point, which means that our pH at the halfway to equivalence point is equal to our pKa, which then means that the pH at that point in time would be 4.74. And that would be all you need to do at that halfway to equivalence point. All right, moving on then, D is after the addition of 25 milliliters of the 0.1 molar sodium hydroxide. Here we have our equivalence point. So this is going to be my hydrolysis of a salt. Okay, and because this is a weak acid and a strong base, I would expect to have a basic salt. Okay, which means my pH should be greater than 7. All right, so I'm going to first go through, there's actually going to be 2 ice tables here that I'm going to do. The first one is to show what is happening when I have the reaction. Oh my goodness. Sorry, that is written horribly. With my hydroxide. Okay, now I know from my earlier calculation how many moles I had. which was 0.002500 moles. So I know that at my equivalence point, those have to be equal, and you could calculate that out if you needed to. So I'm going to be doing minus 0.002500 minus 0.002500 to get 0 and 0. And then over here, sorry, I should have put in 0 for its conjugate at this point in time. And again, this is like, hey, I put in 25 milliliters. What is it at that point? So here I would have produced 0.002500 moles of my conjugate. And then here you have to be careful, because now we're going to actually do the concentration of it. So when you go to divide this, I need to divide by the total volume. So my volume of my acid was 0.0250 liters. That was my weak acid, plus the volume of the base here, 0.02500 liters. That was my strong base. Okay, when you then calculate that and keeping to the 4 sig figs involved, I can see that I have 0.0500 molar of my concentration of C2H3O2. Okay, then this is then going to undergo the hydrolysis step. So I'm going to take that weak base, so C2H3O2. That is going to now react with water to reform the weak acid. Because again, this is acting as a base, so it's going to accept a proton from water, which reforms its conjugate, the acetic acid, and produces hydroxide. Okay, and it's that hydroxide amount that's going to allow us to calculate the pH. So setting up another ice table here. So the concentration I had was 0.0500 molar. I'm going to say 0 here because we actually had 0 from the one above. 0 for the hydroxide, minus X, plus X, and plus X. So I get 0.0500 molar minus X, X, and X. Now, one little thing here is that we only have the Ka of acetic acid, so you do have to find the Kb, which would be your Kw over your Ka. So 1 times 10 to the negative 14th over 1.8 times 10 to the negative 5, which gives you 5.6 times 10 to the negative 10. So then that 5.6 times 10 to the negative 10 would be equal to X times X, which would be 0.0500 minus X. We are going to simplify the denominator there, and then X here, which, be very careful, is equal to your hydroxide, not your hydronium at that point. And keeping with, I had it to 3 sig figs just to keep it consistent with some of the other ones. You would have 5.29 times 10 to the negative 6 molar. And then using that to find my hydronium present in solution, and then finding my pH, which ends up being equal to 8.723. Okay, and I know I kind of flew through that, so just look at one of the extra videos if you need to as well. And that makes sense. This is greater than a pH of 7, which is a good indication that you were doing stuff correct. I only have like a minute left or so, so let me just go over for E. This is after my equivalence point, 26 milliliters of a 0.1 molar sodium hydroxide. That's 1 milliliter of excess NaOH. So I'm going to use that 0.00100 liter using the molarity, 0.1 mole. I have 1.00 times 10 to the negative 4th mole of hydroxide present. I'm going to divide it by my total volume. I had 25 milliliters of my weak acid. This is 26 milliliters of my strong base. That gets me 1.96 times 10 to the negative 3 molar, which is my hydroxide. And if you go through the calculations, you should end up at a pH of 11.292. Okay, so just how many milliliters of excess strong base do you have? Use that to find the hydroxide, and then that will give you and lead to your pH, and that is it.